So let's begin by introducing another concept related to uncertainty, namely that of randomness. In the previous two lectures, we have identified entropy as a measure of uncertainty, and therefore the information revealed when you observe a random variable x generated from a distribution p is this x which is generated from a distribution p is entropy of p, h of p, which I define as summation over x px log 1 by px, because the information, as you remember, was reduction in uncertainty. Okay, so so why is this h of p? Because, well, the uncertainty before the answer was revealed to you was h of p, and after the answer is revealed to you it's 0, and so therefore the information is h of p minus 0, which is just h of p. Okay, but we are calling this a measure of uncertainty, and we defined a problem related to compression to measure uncertainty, or to at least give an operational meaning to uncertainty. But there is another natural notion of uncertainty, namely that of randomness in a random variable. So is a random variable really random? Okay, and how does uncertainty relate to randomness? This is the question we set to answer in this week's lectures. Right. So there are two possible ways to measure how much randomness is there in a random variable x. What are these two possible ways? Here are these two possible definitions. First, you may ask how many random bits are needed to generate the random variable. So this random variable has a specified distribution and you want to generate it, but you only have perfect unbiased random independent bits available to you. How many such bits you need to generate this random variable x? So if you write a computer code where you generate a sample from this random variable x with this PMFP, that computer, how many times will that computer code access this function which generates one random bit? That's one way to think of it. This is a reasonable measure of randomness in a random variable x, or associated with a PMFP. Alternatively, we can think of this definition in green. How many random bits can be generated from? Okay, so needed to generate, and how many random bits can be generated from this random variable x? So how many independent random bits can you extract out of this random variable x? So this is sort of the input. So you give random bits as input to a function, and it gives output as an output. It gives the as the output. It gives a sample from this distribution. Here, what we are asking is, you take as an input x and output random bits. How many bits can be extracted out of this x? These two questions can be thought of as natural measures of answers to these two questions can be thought of as natural measures of uncertainty, natural measures of randomness in a random variable. And we will examine both these definitions this week. So just to make things concrete, let's look at some examples. Let's look at this first example about how many independent unbiased coin flips are needed to generate samples from these two distributions. So before I proceed, I will request you to pause and think about this answer for both these examples. And when you come back, I will be telling you the answer. All right. So for the first question, what we can do, so you need to generate three symbols A, B, C. And A should have probability half, B should have probability 1/4, C should have probability 1/4. Here is one way of doing it by using two random unbiased coins. Okay, first we flip a coin. If it's so we flip coin two times. So if the first one is heads, then we declare A. Okay, if it's tail, then we flip a coin another time. Okay, so if this, so maybe I should depict it better. One second. Yeah. So you flip a coin. If it's heads, you declare A. If it's tails, you flip the second coin. If the second coin is heads, you declare B. Sorry about this. If the second coin is heads, you declare B. If the second coin is tails, you declare C. So what is the probability of A? It's half. What is the probability of B? It's half into half, which is 1/4. What is the probability of C? It's half into half, which is 1/4. So with two coin tosses, I'm able to generate one sample from this random variable with distribution one half, one fourth, one fourth. Now, how about this one? How many coin tosses you need to do to generate a sample from this? If you think of a procedure like the one we have here, what you will soon realize is that to get a probability like 1 over 3 out of coin, unbiased coin, which is probability half, you need infinitely many. You may need infinitely many samples. Okay, so we have to pose this question better, and we can ask questions like how many samples do we need, or how many unbiased coin flips we need on. So how many, right? We said how many on average, on expectation. Okay, that's a better question to generate a sample from this distribution, and that will be the measure of randomness in these two random variables. Let's look at this other question, which is sort of famous. It was studied by von Neumann maybe about 70 years back. So suppose I give you access to samples from this distribution, Bernoulli P, and you want to generate one sample from this unbiased coin. This is the second question, the one we raised here. So this is the first one we saw an example. This is the second one. Then how do you do that? And what is the minimum number of coin flips that you need to do that? Minimum number of coin flips of this kind to do that. So you want to generate an unbiased coin from a biased one. So here is a protocol which actually von Neumann gave, which is not optimal, but it will give you some example. So what you do is you toss the coin 2 times. If both outputs are the same, then you toss it again. But you stop when both outputs are different. So you stop when the outputs are HT or TH. When it's HT, you declare 0. When it's TH, you declare 1, or vice versa, whatever you prefer. Then you can show that condition on the fact that you stop, this probability of 0, 1 is 0 and 1 are equal, and it's just half. Okay? So this is one way to generate an unbiased coin from biased one. In fact, you can compute the expected number of coin tosses from this coin that you will take to stop. That will turn out to be, well, you stop when you have this or this. The probability of this or this is 2 into p into 1 minus p, and therefore the expected number of coin tosses that you need to stop is 1 by 2 into p into 1 minus p. Okay, you can check that. This is a geometric distribution. The distribution of the random variable which indicates the number of tosses after which you stop is a geometric one, and so you will stop after these many coin tosses. The question is this optimal? So the answer to this question is related to how much randomness is there in this random variable. Similarly, the answer to this question is related to how much randomness is there in this PMFP. Okay, and what is very interesting, what we'll see is that the answer to both these questions is roughly the same. It is the entropy of the random variable. So entropy indeed also measures the randomness in a random variable. Okay, so we'll see that in the next part.